Silicon carbide, also known as carborundum, karbERNDM, is a compound of silicon and carbon with chemical formula SiC. It occurs in nature as the extremely rare mineral moissanite. Silicon carbide powder has been mass-produced since 1893 for use as an abrasive. Grains of silicon carbide can be bonded together by sintering to form very hard ceramics that are widely used in applications requiring high endurance, such as car brakes, car clutches and ceramic plates in bulletproof vests. Electronic applications of silicon carbide such as light-emitting diodes and detectors in early radios were first demonstrated around 1907. SiC is used in semiconductor electronics devices that operate at high temperatures or high voltages, or both. Large single crystals of silicon carbide can be grown by the Lely method. They can be cut into gems known as synthetic moissanite. Silicon carbide with high surface area can be produced from CO2 contained in plant material. Discovery and early production. Early experiments, non-systematic, less recognized, and often unverified syntheses of silicon carbide include J. Baselius's reduction of potassium fluorosilicate by potassium. C.It Sar Mansuich Dispretz's passing an electric current through a carbon rod embedded in sand. Robert Sidney Marsden's dissolution of silica in molten silver in a graphite crucible. Paul Schuetzenberger's heating of a mixture of silicon and silica in a graphite crucible. Albert Colson's heating of silicon under a stream of ethylene. Wide-scale production is credited to Edward Goodrich Acheson in 1890. Acheson was attempting to prepare artificial diamonds when he heated a mixture of clay and powdered coke in an iron bowl. He called the blue crystals that formed carborundum, believing it to be a new compound of carbon and aluminum, similar to corundum. In 1893, Henry Moissan discovered the very rare naturally occurring SiC mineral while examining rock samples found in the Canyon Diablo meteorite in Arizona. The mineral was named moissanite in his honor. Moissan also synthesized SiC by several routes, including dissolution of carbon in molten silicon, melting a mixture of calcium carbide and silica, and by reducing silica with carbon in an electric furnace. Acheson patented the method for making silicon carbide powder on February 28, 1893. Acheson also developed the electric batch furnace by which SiC is still made today and formed the Carborundum Company to manufacture bulk SiC. Initially for use as an abrasive. In 1900 the company settled with the electric smelting and aluminum company when a judge's decision gave priority broadly to its founders for reducing ores and other substances by the incandescent method. It is said that Acheson was trying to dissolve carbon in molten corundum and discovered the presence of hard blue-black crystals which he believed to be a compound of carbon and corundum. Hence carborundum. It may be that he named the material carborundum by analogy to corundum, which is another very hard substance. The first use of SiC was as an abrasive. This was followed by electronic applications. In the beginning of the 20th century, silicon carbide was used as a detector in the first radios. In 1907 Henry Joseph Round produced the first lead by applying a voltage to a SiC crystal and observing yellow, green and orange emission at the cathode. Those experiments were later repeated by O.V. Lossev in the Soviet Union in 1923. Natural occurrence. Naturally occurring moissanite is found in only minute quantities in certain types of meteorite and in corundum deposits and kimberlite. Virtually all the silicon carbide sold in the world, including moissanite jewels, is synthetic. Natural moissanite was first found in 1893 as a small component of the Canyon Diablo meteorite in Arizona by Dr. Ferdinand Henry Moissan, after whom the material was named in 1905. Moissan's discovery of naturally occurring SiC was initially disputed because his sample may have been contaminated by silicon carbide saw blades that were already on the market at that time. While rare on Earth, Silicon carbide is remarkably common in space. It is a common form of stardust found around carbon-rich stars, and examples of this stardust have been found in pristine condition in primitive meteorites. The silicon carbide found in space and in meteorites is almost exclusively the beta polymorph. Analysis of SiC grains found in the Murchison meteorite, a carbonaceous chondrite meteorite, has revealed anomalous isotopic ratios of carbon and silicon, indicating an origin from outside the solar system. 99% of these SiC grains originate around carbon-rich asymptotic giant branch stars. SiC is commonly found around these stars as deduced from their infrared spectra. Production. Because of the rarity of natural moissanite, most silicon carbide is synthetic. It is used as an abrasive, and more recently as a semiconductor and diamond simulant of gem quality. The simplest manufacturing process is to combine silica sand and carbon in an Attribution graphite electric resistance furnace at a high temperature, between 1600 degrees Celsius and 2500 degrees Celsius. Fine CO2 particles in plant material can be converted to SiC by heating in the excess carbon from the organic material. The silica fume, which is a byproduct of producing silicon metal and ferrosilicon alloys, also can be converted to SiC by heating with graphite at 1500 degrees Celsius. The material formed in the Attribution furnace varies in purity, according to its distance from the graphite resistor heat source. Colorless, pale yellow and green crystals have the highest purity and are found closest to the resistor. The color changes to blue and black at greater distance from the resistor, and these darker crystals are less pure. Nitrogen and aluminium are common impurities, and they affect the electrical conductivity of SiC. Pure silicon carbide can be made by the so-called Lely process, in which SiC powder is sublimated into high-temperature species of silicon, carbon, silicon dicarbide, and a silicon carbide in an argon gas ambient at 2500 degrees Celsius and redeposited into flake-like single crystals, sized up to 2 × 2 cm, at a slightly colder substrate. This process yields high-quality single crystals, mostly of 6H SiC phase. A modified Lely process involving induction heating in graphite crucibles yields even larger single crystals of 4 inches in diameter, having a section 81 times larger compared to the conventional Lely process. Cubic SiC is usually grown by the more expensive process of chemical vapor deposition. Homeopataxial and heteroepitaxial SiC layers can be grown employing both gas and liquid phase approaches. Pure silicon carbide can also be prepared by the thermal decomposition of a polymer, poly, under an inert atmosphere at low temperatures, relative to the SiC.It process. The pyrolysis method is advantageous because the polymer can be formed into various shapes prior to thermalization into the ceramic structure and properties. Silicon carbide exists in about 250 crystalline forms. The polymorphism of SiC is characterized by a large family of similar crystalline structures called polytypes. They are variations of the same chemical compound that are identical in 2 dimensions and differ in the third. Thus, they can be viewed as layers stacked in a certain sequence. Alpha silicon carbide is the most commonly encountered polymorph. It is formed at temperatures greater than 1700 degrees Celsius and has a hexagonal crystal structure. The beta modification, with a zinc blende crystal structure, is formed at temperatures below 1700 degrees Celsius. Until recently, the beta form has had relatively few commercial uses, although there is now increasing interest in its use as a support for heterogeneous catalysts, owing to its higher surface area compared to the alpha form. Pure SiC is colorless. The brown to black color of industrial product results from iron impurities. The rainbow-like luster of the crystals is caused by a passivation layer of silicon dioxide that forms on the surface. The high sublimation temperature of SiC makes it useful for bearings and furnace parts. Silicon carbide does not melt at any known pressure. It is also highly inert chemically. There is currently much interest in its use as a semiconductor material in electronics, where its high thermal conductivity, high electric field breakdown strength and high maximum current density make it more promising than silicon for high-powered devices. Electrical conductivity. Silicon carbide is a semiconductor, which can be doped N-type by nitrogen or phosphorus and P-type by beryllium, boron, aluminium, or gallium. Metallic conductivity has been achieved by heavy doping with boron, aluminium or nitrogen. Superconductivity has been detected in 3C-SiC-Al, 3C-SiC-B and 6H-SiC-B at the same temperature of 1.5 K. A crucial difference is however observed for the magnetic field behavior between aluminium and boron doping. SiC-Al is type 2, same as C-B. On the contrary, SiC-B is type 1. In an attempt to explain this difference, it was noted that C-sites are more important than carbon sites for superconductivity in SiC, whereas boron substitutes carbon in SiC, Al substitutes C-sites. Therefore, Al and B, C, different environment that might explain different properties of SiC-Al and SiC-B.